has two kinds. One is reductive and oxidative. Reductive is more of a controlled oxidation. Oxidative is a complete oxidation. So in case if you have any group like this, double bond, and you treat that with O3 in the presence of zinc and H2O, first and second, this will end up at ketone, while this will end up at aldehyde. So the bond breaking is observed to happen this way. This is what we have learned from reductive ozonolysis. Last we did was the example of orthoxylene, where the bond breaking will take place and we will get three different types of products, right? So one is this double bond formed here, one is here, and one is here, which is glycol. This is alpha oxo aldehyde and beta diketone. So these are the three forms we got. So the idea is break the bonds and attach with that a double bond O. Okay. Now, usually how the questions can be asked is if you would be given like products and you're supposed to check what are the type of hydrocarbons from which these products could be possible. For example, find the reactants which can possibly give these products on ozonolysis. Suppose it was said to us that 2H2O plus this cyclobutanone and double bond O with double bond O with CHO. These are the three products which have been seen on ozonolysis. So obviously this is reductive ozonolysis. So how do we find out the possible products? We will do wherever there was a double bond here, we'll try to just connect them and see. Correct? So how many possible products we can get? For example, if I take this molecule and try to connect 2 moles of CHO on this side and this side, let's say. So we can have here as a double bond. And what if at all I have CH2? Here, check out where I'm pointing out this position. If at all there was a double bond, what you would have done, you would have broken this, and one would have come as formaldehyde, the other would have remained it as double bond O here. So that's how we are making a connection. That is where one connection I can make. Another connection is on this side. We have this as CHO here, so I can make this double bond CH2. So here I can make one double bond and from here we have this, and then I can make a double bond with this cyclic form. So you could see if I break one here, so I'll get 2 moles of formaldehyde, one here, I'll get this molecule, and the rest of this molecule would be this. So this is one possibility. So reactant 1, R1, reactant 1, like that. What is the other possibility? I can just change the direction here, like this. If at all I make CH2 here, double bond group here, and here I can make a double bond. So this is one form. Or I can change this cyclobutanone here with double bond and double bond here and double bond here. Correct. So that way, these three combinations, even if you break this one or this one or this one, so we'll get all these three types of reactants. In case if there is any cis trans, unfortunately there is no cis trans here, but if there is any cis trans, you just have to find out that also and tell how many total reactants are possible to give these products. This type of synthesis, that is from products, if you are going towards reactants, that is towards the alkene, it is called retrosynthesis. So question could be asked, make the retrosynthesis of respective hydrocarbons which can give this particular carbonyl groups. So how we can do? I'll take this as the main group and try to put all the double bonds closing with it. So let's say this is how it is. I can put one CH2 here which was connected to give this formaldehyde, and this side it could give one ketone this way. This is one product. Another product is here I can have this, and here I can have this double bond with this methyl. So these two are possible, and you can see this has a chiral center, this has a chiral center here. So two of them can come here and 2 of them can come here. So total 4 reactants are possible to get these products. Let's come to oxidative ozonolysis. Okay. Just the extension of this oxidation, where we are stopping at aldehydes. If you do not stop at aldehydes and you go up to acids or any other carbon dioxide form, then we'll get it as reductive ozonolysis. Okay. Let us see first. If we have CH2 double bond CH2 and we are making a reaction with O3 and there is no zinc that has been taken which controls the nascent hydrogen. So in that case, first 2 moles of formaldehyde will form, which will oxidize to 2 moles of acids, which can further oxidize to form carbon dioxide. So we'll get 2 moles of carbon dioxide. This is what you would see. Okay, everyone. Similarly, so the oxidation will eventually stop at carbon dioxide. Similarly, if we take CH3, CH double bond CH2 and we treat that with O3 and H2O. So this is an oxidative ozonolysis. First we would get acetaldehyde and formaldehyde, which both undergoes further oxidation to give acetic acid and carbon dioxide. Acetic acid and carbon dioxide. Suppose if there are alternate double bonds, like we have CH, CH double bond CH2, and I'm treating that with ozonolysis. So here both will break. Two sides we have these 2 carbons, and then we have oxalic acid, that is COOH and COOH plus 2 moles of carbon dioxide. Now, up till this point, these oxidations are quite similar to that of what we do it for KMnO4 also. Remember, for KMnO4, K2Cr2O7 on heating, we were getting the same products only. These were all oxidative products. But their oxalic acid is not stable. That will further convert into carbon dioxide. Okay, there we check that oxalic acid won't be present. It will further convert into carbon dioxide. Reason being, it would undergo reason being, this CO2 is because when you are using that with KMnO4, see, when you are using that with KMnO4 heat in acidic medium. So first COOH will form, this 2 CO2 will form, but because you are heating it, so on heating, this can further undergo oxidation to give 2 moles of CO2 in the presence of KMnO4. Ozonolysis usually happen at a low temperature, because you see ozonoids are usually unstable. For these ozonoids to form, we require a very low temperature. So because they usually happen at low temperature, we can isolate this oxalic acid, which is not the case in KMnO4 or K2Cr2O7 cases. I think you understood the difference between KMnO4 and ozonolysis. Fourth, if we take benzene, yes, Vita, with conjugation.
Yes.
Huh.
If there is total number of products.
That would be depending upon the canonical given to you. Okay, don't you yourself take a canonical. Don't take this canonical, because this is the least contributing one. Okay, you know that the percentage amount of this would be very, very less, not even 0.1%, because this is a major product. Okay, so don't do any kind of this thing resonance here unless it is equivalent resonance, like in benzene. Okay, see, that is what I'm talking in benzene here. So in case of benzene, if you observe, benzene can give reaction with ozonolysis, which means O3, 2 and H2O. So what does it form? It forms 3 moles of oxalic acid. Okay, while what about the reaction with KMnO4, H plus and heat? No reaction. Got it? Here we have seen with benzene, it won't make any reaction. And KMnO4 usually operates only when you have, localized pi bonds, correct? Or for example, here, this is less localized pi bonds because they do not give any kind of equivalent resonating forms. But here there are very highly delocalized forms. So in those cases, KMnO4, K2Cr2O7 doesn't make a reaction. Clear, everyone? So with benzene, don't take reaction with KMnO4. I suppose that point is clear, everyone. Right. So let me take a few more cases. So just based on what it is given, you must accordingly take the product. Suppose if this is how it is given and reaction is with O3 and H2O, which means it is oxidative ozonolysis. Since it is oxidative ozonolysis, bond breaking will happen on this side. Bond breaking will happen on this side here with H. First, this is the reductive ozonolysis, which will further oxidize. Keto doesn't happen. For keto group, nothing will happen. So it will remain like keto form only. But if you see here, it is, see the number of carbon, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So on the 7th carbon, we will get it as acid. And on the 2nd carbon, we will still have a keto form retained. This is what happens with. So I hope you all got an idea like what is the reaction that is happening. Same way, if we take double bond this way and here, and we make oxidative ozonolysis, break the bond there. So both sides, if you break the bond, we would get this kind of a molecule here with double bond O here, double bond O here. With this side, it is becoming COOH. This is the final product. Well, we have studied about carbene before. Carbene is a species which would act like an electrophile. It would have an empty orbital, or they would exist in two forms. One is as a singlet, the other one is as a triplet. Singlet will have one pair of electrons and empty orbital, while triplet will have two unpaired electrons this way. Preparation, how to prepare, we have seen it earlier, when we were discussing about carbenes, intermediates. Now, let us see what are the type of reactions they will see. Wherever there is a double bond, they get, inserted or get added, like CH2, CH2. If they've been treated with CH2N2, diazomethane, in the presence of light or heat, so CH2 gets added and you'll get this product plus N2. Similarly, if you have cyclohexene and CH2N2, HNu or heat, it would get added to give this product. Alright. Now, let us see the stereochemistry of this. Stereochemistry. In case of singlet, if it is singlet, then it would be stereospecific. Stereospecific. For instance, if you have a cis molecule and I treat that with CH2, this is the singlet form, then the product which you will get will be only erythrochine, which means you will have CH3 on the same side, H on the same side. So we'll get this as erythrochine. How the mechanism favors here? Imagine this double bond as, two pair of electrons. And then we have CH2, correct? So here we have a CH2 molecule. So as soon as the CH2 with a lone pair approaches here, correct? So this pair of electrons will rearrange such a way, this electron would be found at one place, and here it is like an empty orbital. And this side, here we have electrons, and this side we have an empty orbital. So this will fill here, this pair will fill here, giving it to the addition from the same side. So this is a transition state, it will go through CH2 and forms cis product. Here everyone. So you could guess what is happening here. Cis is making a syn addition, so expected is erythro. Suppose if at all I would have taken trans and then I would have added singlet here, singlet, then what is the product I will get? 3O. So CH3 here, CH3 here, H and H here. This is what we will get. Since you can see this has chirality being shown, which means it would have its mirror image also, giving the final product as a racemic mixture with CH3 here, H here, CH3 here, and H here. Alkene is stable. There is an empty orbital is coming, right? Electrophile is approaching. That's why it is reacting. Octet completion is always most favorable. Next, let us see about triplet. So in case of triplet is non-stereo specific. Non-stereo specific. Okay. So why it is, you can see, write it here only. If I take a cis molecule, suppose this is a double bond, and CH2 is also coming as if it has one double bond here and one single electron here and one single electron here. So these two electrons will terminate here first, correct? Now what would happen? As soon as this termination takes place, first it won't happen like once this bond is forming, at the same time this bond will form. So usually what has been observed, that first a bond will form here, forming as a radical this side, and CH2 as a radical here, correct? Now depending upon the solvent, the percentage of rotation would be dependent on, which means now it has formed a single bond, so it can undergo rotation also. So since it undergoes rotation, I can have with and without rotation here. So which is without rotation, this CH2 will attack here like this, which means these two radicals will terminate. Or with rotation, if you observe, this would go up, or I can say this would go up here, and CH2 would come down here, and radical is here. So these two will terminate. So something like this can happen. Clear? So both formation are observed in this case. Reason being, first, CH2 itself is existing like a radical, diradical, because it has two radical cases in case of triplet. So these two would immediately terminate to form a bond here. As soon as the bond forms, there is a chance for this bond to start rotating. So with or without rotation, you will get the forms. Clear? So after rotation also you get this product. So and hence we cannot say it is completely stereo specific. It would have some non-stereo specific character in it. So if it was a singlet given, you'd probably write one product here, only one product in this case. But in case of triplet, whether you take cis, whether you take trans, both occurrence can be possible. That's why it is non-stereo specific. I guess this is clear, everyone. Now, when it comes to singlet forms and triplet forms, usually singlet form is more stable. Sorry, triplet form is more stable when it is with hydrogens. Let me write as a stability. If you write stability, usually this triplet form is more stable than singlet form. But if it is halogens, in case of halogens, because this lone pair can completely participate the lone pair from chlorine can donate it to carbon, so it would expect to keep the orbital empty like this. It would have one orbital with one electron here, chlorine and chlorine. So chlorine's electron can be given as a back bonding. So hence they would exhibit more stability in the singlet form rather than being in triplet form. This is the stability. Okay. Now in generally, if we take, let me take one reaction here. For example, chloroform. CHCl3 in the presence of tert butoxide, potassium tert butoxide. In tert butoxide, this acts like a base, extract the proton from here, creating CCl3 minus plus this OH. Now CCl3 minus, if you see the structure here, this is a pyramidal structure. This pyramidal structure would have repulsions between the lone pairs of chlorine here, and it won't be stable for a long, so it would break into this carbene molecule, dichlorocarbene. Now the dichlorocarbene which is formed is the electrophile, and this electrophile will get added onto any particular double bond. Suppose if there is a double bond here, okay, and that double bond, if you bring this chlorine closer, will undergo first with the insertion. So it will undergo an insertion like this, where dichloro get inserted with two chlorines present. Okay. Now you can see chlorine is a good leaving group. So when there is a good leaving group present and there is a ring strain developing here, okay, so what it can do, it will try to become more stable by donating this bond and releasing chlorine out. So here it can release chlorine out. So what is the product you can get? We will get this as, you can see this bond has broken, so it has become 6-membered ring now. So you can, I'll give you the numbering 1, 2, 3, 4, 5, 6. And on the first carbon now we have one chlorine and the other chlorine has left. So this is 1, 2, 3, 4, 5, 6. On the sixth chlorine I had carbocation form, and between 1 and 2 double bond has formed. Correct. So now the elimination would take place because this Cl minus which has left will extract the beta hydrogen from this 5th position, and we can get a double bond like this. Okay, students, I hope you understood this point. So there are two products we can get. One is this product, one is this product. Slightly increase the temperature, the percentage of this will increase. If it is at a lower temperature, this will also have sufficient, form. So at around room temperature, you will find this product, which is this one, dichloro, cyclic product, around 35%. But this product, which is more stable here, this will be around 65%. So if the major product is asked, this is the major product. Okay, everybody understood this point? Make a note. On a similar lines, let me do one more question. If there are two double bonds already existing, and we react this with CHFCl2, and tert butoxide is being taken, K+. Then what is the product that is expected? First reaction is acid-base reaction. This is a strong base. There is a protic hydrogen here. So first reaction is tert butoxide trying to extract the proton from here. So it would get this as OH plus CFCl2. This is 2, CHCl2 minus. Second step is that CFCl2 minus would slowly start giving Cl and F with Cl minus. F is a weak leaving group, poor leaving group. Chlorine would leave here. So you would got an electrophile. So the third step is attack of double bond on the electrophile. So CCl, F, empty orbital is present. So as it attacks, first it will get inserted this way. We'll have fluorine and chlorine. Correct. Already there is a double bond form. Already there is one double bond form existing, and this double bond now has become the cyclic form. And you know that when it comes to stability, this bond will break and Cl will leave, because Cl being a better leaving group. So as it leaves, 6-membered ring is formed. Already there is a double bond. One more double bond will come with fluorine here. Correct. Fluorine here and positive charge here, which will be extracted. Tert butoxide can extract proton from here, and we will get benzene form. So the final product, if you observe, is fluorobenzene. So this is the product formation here. The product for this reaction is fluorobenzene. Next example of carbene reaction is a name reaction called Simon-Smith reaction. Simon-Smith reaction. Well, this is not for JEE. Really, this is slightly out of the syllabus. Okay, only for internal exams. And Simon-Smith, same is the product here, double bond with CH2I2, in the presence of zinc copper couple. Zinc copper couple, if you take, you would get a product this way. So this is the product which is formed. Right, so what is the product formation here? See, first, when the reaction takes place, we have CH2 here, we have I and iodine. So due to delta positive present on it, zinc will provide electrons, and these electrons will start hitting onto carbon, creating delta negative charge, in fact negative charge plus I minus charge. Zinc 2 plus will have strong polarizing power, so it would be able to hold both of them covalently. Okay, so you would get a product something like this. We have ICH2, zinc and iodine, where this has delta negative, and this would have delta positive. So this formation is seen. Now you can see that this CH2 minus is like almost delta negative charge on it, correct? But iodine is a better leaving group, so that can leave. Sorry. So that makes it an initiation for the reaction. This double bond, CH2, I is here with Zn and I. So this, as soon as this attacks, I minus would leave. Okay. And so CH2 minus was there, which was being drawn away by iodine. That negative charge has been drawn away by iodine. So as soon as I minus leaves here, zinc will get connected with this, CH2 will get connected with this. So here we will get this type of a connection, and ZnI2 is formed. Okay, students. So only you just need to know what is the final product. There is no mechanisms that have been asked from this area. For example, if you have a double bond here, this way, we treat with CH2I2, zinc copper couple, the product formation would be this one, spiro. The spiro formation is observed. In case if you have allyl substitution, what is the product that is formed? First of all, you must always analyze what is an allylic position. This is an allylic position. So a carbon which is sp3 hybridized and adjacent to a vinylic carbon. So which clearly tells that these two are vinylic carbons. Right. Now, usually when we take a double bond here and treat that in the presence of Cl2 and HNO, sorry, we could see an addition product happening here, which means this pi bond can break into radicals and we can see chlorine get added. Correct. At the same time, we can see a substitution can happen as well. Whether this product is major or this product is major depends upon the temperature. Because on increasing temperature, addition reactions are less favored because these are exothermic. Correct. When you see the double bond, if you add anything on a double bond, it is always exothermic. Since it is exothermic, on increasing temperature, this product would be minor and substitution will come as the major product. So if you have Cl2 and HNO, or this is more preferred when you have chlorine and heat around 300 degrees and above. 300, 500, question could be given in any form. So when you react with this, we would get, substitution as the major product and addition as the minor product. Got it? See the mechanism now. Cl2 on reaction with H2 or heat will break into two Cl dots, and this hydrogen which is present, okay, when you treat that with Cl dot, we'll try to give a more stable radical here. Let's HCl is formed. So this is the propagation step. So the propagated radical again reacts with Cl2 to form substituted case plus Cl dot. So that's how the major product will be formed. And this major product can be improvised as long as you keep increasing the temperature. Now, in case of chlorine, identifying exactly at this point is also difficult, because if you remember the ratio of chlorine substitution at primary, secondary, tertiary, in all of those cases, we have seen it could give, more reactive cases rather than more selective cases. But in case of bromine, it will be highly selective. So here the major product which is coming may also have some other parts, which means substitution may also have some small traces of this. Here, some chlorine could be found here also. Anyways, I'm not writing that because we are not concerned for those products here. We are only worried about whether we can get allylic products or not. But in case if you take bromine, there it is highly selective. So bromine will definitely give you almost 99.9% of only allylic substitution as the major product. So for example, if we take this radical propene and treat a molecule propene with Br2 HNu or Br2 in around 300 degrees centigrade, got it? Then we will get Br here. Now imagine the concentration of Br dot is even decreased. Okay, if the Br dot concentration decrease, it would become even more selective because there are no more extra Br which has a tendency to attack at any other position. Got it? That is done by a reagent called NBS. Reagent NBS, N-bromosuccinimide. So C double bond O here. This is an amide group. Okay, imide group. When you have this, two connections with bromine. This is N-bromosuccinimide. So N-bromosuccinimide will always have impurity of some HBr. It will always have some impurity of HBr. So when you take N-bromosuccinimide, along with that there would be some small impurity of HBr. Because it has small impurity of HBr, what we can say, this N-bromosuccinimide, when you heat it, got it, because there is a small source of HBr, it can form succinimide here, NH, plus a small quantity of Br2 will be released. And this Br2 will become the source, in the presence of HNu or temperature, to give radicals. And the concentration of the radicals is less, so it would be highly selective product which you will get. So in exams, if NBS is given, definitely you will have to go for substitution. So therefore, if at all I take an example like this and treat that with NBS, it is understood that if it is written NBS, it would have impurities, it would form this, and Br radical is formed. Everything is understood in this if you write NBS. So the product formation will be Br here plus HBr. Okay, everyone? Right. Now, in case if this carbon has isotopic form, let's say, be this example A, example B, this has an isotopic carbon, and we react with it as NBS. We know that first a radical is forming, and then again it reacts with Br2. So when a radical is forming, it can always show resonance. So this will come. So two products, two bromo allylic substitution product can be appeared here. Star is here, Br here, star is here. So these two products can come. So what do you need to find out the number of products? First, you draw the allylic radical and see how many radicals we can get like that. Because by resonance, we can get a lot of radicals. From there, you will find out how many total products we can get. So what is the first thing we'll do? We'll try to point out the radical positions. One radical position is here. One radical position is here. But both of them are identical only, no? Structurally, both of them are identical. So you can take only one of them. Next, this can undergo resonance stabilization. So double bond can come here. Radical can go up. Okay. Since they are structurally same, I'm not writing this anymore. So which means I can just simply put it here as the resonance form. So these two are the radicals which you can expect to form. Now from here, Br will get, when you treat with Br2, in NBS there is Br2 already. So don't think, sir, where did Br come from? So here we'll get one product with this Br2. We would get another product, Br. Now if you observe, this carbon has become a chiral center. So which means we'll have two products here. Here there is no chiral center, so one product. So total how many products we can get here? Total 3 products. See what are the distinct radical positions we can get. Here there is one radical position. There is one radical position, and there is one radical position here. So these 3 distinct radical positions we can get, and their respective resonance canonical forms also. So double bond here, radical here, double bond on this side, radical here, double bond here, radical here. Guess all of you got that. So how many distinct radicals we have here now? See, 1, 2, 3, 4, 5. Why didn't I count this? These two are same. Check out. Okay. So we got 5 distinct radical. So on this 5 distinct radical, let me make 5 bromines. So what are the products we can get here? So 1, I'll remove the radical position here. So we'll get 1 Br here. So 1 Br here. So 1 Br here. 1 Br here. Br here. Br here. Okay. But since these two are same, I'm removing that. Okay. Now I'll count the total of them. How many do we have? So these are the products which we got. Is there any chiral center in the first case? Yes, it is. So which means we'll get 2 products from here. Is there any chiral center in the second case? No. It's only 1 product. Is there any chiral center here? Yes, it is. So we'll get 2 products here. Is there any chiral center here? Yes, it is. You can see there are 4 different groups here. So which means I can get 2 products here. And there is a chiral center here. Yes, it is. So I'll get 2 products. So total products, how many? Total products you will see is 2, 4, 6, 8, 9. So total 9 products you'll get. Suppose if there is only monobromination I have to do, then reactivity order for monobromination. Okay. So that depends upon the more stable radical formation. Suppose if you have CH2, CH3 here, and I'm trying to compare that with CH2 double bond CH2, trying to compare that with CH3 CH double bond CH3, and CH3 CH double bond CH CH3 and CH3. Let's say I took this as A, B, C, D. So which one will have more rate? You know, by NBS. Do it by NBS. Which one will have more rate here? This has H here. See everyone?
It's a D, sir.
Right. So D, then C, then B, then A. Imagine the same rate was asked as a Wilkinson's hydrogenation. Correct? If at all I use the same reactivity order using maybe palladium with carbon activated or Wilkinson's catalyst, right? Any of these is taken. How would be the order?
It's a reverse.
Reverse. A, B, C, D. Because there, crowding is very important. Less the crowding, more is the reactivity. Right? So this is the rate of hydrogenation. Okay. So I'll give you one reactant and only one equivalent. So you got to find out the product. Yes, tell me. Which is less hindered here, less steric here, above one, right? So the reduction will take place here. This double bond remains. This is the first product. Br2. Electrophilic addition will always take place at the more crowding area, which means it should have a stable non-classical carbocation. Stability should be more. So it would have Br here and Br here. Non-classical carbocation addition will be more. Next, Br2H2O. Same at the same location, except that, you know, Br will be added at the terminal position and OH will be added at the stable non-classical carbocation. Next, MCPBA will also add at the more donating species. So which is more donating species here, this side. So everywhere you have electrophilic addition, always go for more substitution area. Next, HBr1 equivalent. So we would have double bond here and HBr will get added here. So we'll get Br to get added here. That is at the tertiary position. So that is where it will get added. NBS, very interesting one. All right. So which is a more stable radical position here. Okay. So you can see below, this is a tertiary one, which is a more stable radical position. So Br will get added here. Double bond would be here. Next, KMnO4. Right. So substrate addition will happen always at more substitution plus. See your answers, everyone. So next reaction, what you'll observe is allylic oxidation. As a reaction, this is very important because this has been recently asked in JEE 2-3 times. Done. See what is happening here. In allylic oxidation, when you have an alkene at the allylic position, if you treat with selenium dioxide, then it gets hydrated such a way that OH will get substituted there. Mechanism is not there for syllabus, but nevertheless, I'll just give you an idea about how it happens. Suppose if you have double bond here with hydrogen here. Now imagine this is the isotopic carbon, okay? Just to make sure you understand the distinction where it is getting added. Now, when you take selenium dioxide, which is this way, so the pi will attack on the empty orbitals of selenium, and this pi will extract the proton. And as it extracts the proton, the bond between carbon and hydrogen breaks, and it will make a double bond formation. So you will get a double bond form here with this bond formation is observed with selenium. Now, as it becomes, this side you can see it has become OH, this oxygen and H has become OH, and then there is a double bond O present. The lone pair present on this oxygen will again attack on this side of the carbon, so that this will move here. See, check out the isotopic carbon where it is. As it moves, selenium will take away its electrons, forming again a double bond here, and we got an oxygen connection on this side with selenium here with OH formation. This is what we got. And from here, let me just take it down. Yeah. So from here on hydrolysis, we will get this part becoming OH. This is the isotopic carbon plus SCOH twice. So this is the final product which is formed. In case if there is a double bond here with substitution, then SCO2 and heat and H2O hydrolysis. See, H2O may not be mentioned. You got to understand that SCO2. After that, we are anyway doing hydrolysis. Okay. So here there are two allylic positions. You can say this is one allylic position, this is one allylic position. Correct. So the attack on the more allylic position is favorable. Correct. So if you remove hydrogen from here, oxygen can attack on that part better compared to that of this side of the carbon. So the major product which you will get, these are simultaneous steps. No intermediate radical is formed. You can see all arrows are going simultaneously.
I mean, there are here
more substituted, always added, more substituted. Please remember it that way. These are not very, what do you say? Mechanisms which are needed for the exams. If there is any isotopic form here, this side, let's say there is isotopic form like this. So the other side, there is no hydrogen. So that side it won't happen. So where is the product that will form? It will form here only, OH. This is the product.